All right, the time has finally come here in section 5.5 to prove the triangle angle sum theorem, which of course says that the sum of the angles of a triangle is 180 degrees. Any triangle, any size, any shape. We're about to see how this is done. And we'll also prove a number of corollaries of the triangle angle sum theorem. So a few quick definitions that'll come up in our results. First of all, we say that a right triangle is a triangle that has at least one right angle. An obtuse triangle is a triangle that has at least one obtuse angle. And an acute triangle is a triangle that has three acute angles. Now, if you paid attention to what I just said, you might be troubled by how precisely I framed those definitions. I said, for instance, that a right triangle has at least one right angle. I imagine that someone might respond to me, well, isn't it the case that a right triangle has precisely one? A right angle couldn't have more than one, and I will say, yes, of course, this is true. But I will also add that this should not be part of the definition because it is provable. We are able to prove that a right triangle has precisely one right angle. Okay? And we will prove it as a matter of fact. And this is part of our general practice. We say only so much about an object in its definition that allows us to identify it, to reliably pick it out, to distinguish it from other objects. And we do not pack into that definition any information that we are able to prove. So, the triangle angle sum theorem. How will this get proven? Well, I often say this to my students, that I wish that when you first walked into this class, I could have pressed a button and made you forget everything that you thought you knew about geometry. Forget those theorems that had been introduced to you before you came into this class, like the Pythagorean theorem, perhaps, which we will eventually prove, and the triangle angle sum theorem, which you probably also saw before you came into this class. And the reason for this is that when you encounter those theorems, since you're familiar with them, since you've been told that they're true, you miss the surprise that should be felt about them. And I think this is in particular true of the triangle angle sum theorem. I imagine a conversation that one might have with, I don't know, a bright, perhaps third grader who knew what a triangle was, but had never encountered the triangle angle sum theorem, but was also familiar with the idea of a degree, what degree measure meant for angles. And if one were to ask them, like draw a bunch of triangles up on a board and, ask them, it's like, what do you think the angle sum is for this one and then that one? And I don't think they'd know. They might, attempt to measure it and make a guess about that. And then if you were to ask them the question, well, do you think it's the same for all of these triangles? Perhaps you have big ones and small ones and some that look equilateral and some that are just average, ordinary triangles, nothing special about them. I suspect that they would say, and students have confirmed this to me when I have asked them to think themselves into such a position, I think they would say, probably not. Probably, this tiny little triangle differently shaped than this big triangle over here, the angle sum would be different, right? So the triangle angle sum theorem, if you hadn't been introduced to it before, I think would come as a surprise, maybe as a shock, and I wish that you could experience that. But oh well. So let's now talk about how actually it would be proven. And this is one of the most extraordinary conductions, I think, in elementary Euclidean geometry, what we do here in this class. That it comes as a surprise, I think, that this would have anything at all to do with parallels. Because when one thinks about a triangle, of course, well, one knows that none of the sides is parallel to any of the others, and one might then suspect or conclude that, whatever comes out of the study of parallels, it just wouldn't have any relevance at all to the triangle, to the question of the sum of the angles of a triangle. But it absolutely does, okay? It absolutely does. And I'll tease you a little bit here. When we talked about the Playfair postulate, the parallel postulate, I suggested that you go and read around about the history of that postulate, and you might have come across the idea of a non-Euclidean geometry. That's a geometry in which we don't have the parallel postulate. We have some alternative instead, and there are possibilities for that. And these alternative geometries, the non-Euclidean geometries, this isn't even true. Anyway, so let me show you how it is that parallels are relevant to this, and parallels make this possible. And as a matter of fact, if you don't have parallels in the behavior that we have seen in Euclidean geometry, you can't even prove this. So we're given a triangle. The triangle in this case is triangle ABC. and we wish to prove that the sum of its angles A and B is C is 180 degrees. Now, recall, okay, this is talked about in the previous slide. Recall that if we're given a line and a point not on that line, we may, through that point, construct a line parallel to the given line. This is the absolutely crucial move. Okay, so what you do is this. You pick a vertex, and through that vertex, you construct a line parallel to the opposite side. So how about through B, we construct a line parallel to AC. Okay, so there we go. So it would look something like this then. So we began with the construction step. So through B, construct a line parallel to AC. Okay? And then think about what happens. Okay? Well, we get some angles, right? So we get the angles 1 and 2. And then let's think about relationships between them. For the rest of this, I'll just talk through it. Well, we've got parallels now, right? That line that we constructed through B is parallel to AC. And then look at angle 1. Perhaps color code this. Look at angle 1 and the angle at A. They're alternate interior, so they must be equal to one another. Now look at angle 2 and the angle at C. I'll also color code that. So the angle at 2 and the angle at C. They're alternate interior, so they must be equal to one another. So let's actually mark this, the equality that must follow. So we have a pair of equal angles, and then we have a second pair of equal angles. Now ask yourself this. What's the sum of that angle? How about purple for B? What's the sum of those three angles at B? Okay. Well, they're what we called back in a previous chapter a linear tuple. There is, as a matter of fact, three angles that together form a line. So the sum of those three angles, 1 and 2 and B, is 180. But 1 is equal to A and 2 is equal to C, so it must follow that A and B and C sum up to 180 degrees. And that's it. Okay. You construct the parallel, you get equal alternate interior angles. You notice that you have a linear triple, and then you just substitute and you get your result. That's it. That's all there is to it. So let's now prove some corollaries. Remember that that's a mathematician's term for like a relatively quick and simple result that follows from a theory of significance that has already been proven. Corollaries are just more theorems, but to call them a corollary sort of gives the position in the system that you build. So here's one, the third angle theorem, which says this, that if two angles of one triangle are equal to two angles of a second triangle, the third angles must be equal as well. This should seem fairly obvious now. If the sum of A and B and C is 180, and the sum of D and E and F is 180, then it must follow that C is equal to F. I'll let you think on the worksheet about the exact algebra that's involved here, but it's really quite simple. And next result. You might recall that we had the triangle exterior angle inequality, which says that an exterior angle of a triangle is greater than either of its remotes. We're now able to prove a stronger result. Okay, the stronger result is the triangle exterior angle equality, which says that an exterior angle of a triangle is equal to the sum of its two remotes. So here's our setup. We've got triangle ABC with exterior angle BCD. So here's the exterior angle BCD. And we wish to prove that it's the sum of its two remotes, which of course are angle A and angle B. And how would we do this? Well, consider the relationship of, I'll mark it in red, of BCA to BCD. Consider the relationship of BCA to BCD. They're a linear pair, so they sum up to 180 degrees. But let's also ask about the relationship of the sum. Pay close attention to the way that I put this. What is the relationship of the sum of A and B to angle ABC, the red angle? Once again, the sum is 180 degrees. So both the sum of A and B and BCT sum to 180 with BCA, which means that they must be equal, just to form the same supplements theorem. All right, so there's our stronger result. Next result is this, is that every triangle has at least 2 acute angles. Okay, every triangle has at least 2 acute angles. And how would one prove that this must be the case? I suggest that you approach this indirectly. That is, assume that a triangle has either 1 or none acute angles. That would be the negation of what you wish to prove. And then think about that triangle. The triangle with 1 or none acute angles. That would be a triangle that has either 2 or 3 angles that are right or obtuse. And think about the sum of the angles of a triangle that has 2 or 3 angles that are right or obtuse. It must exceed 180 degrees. Okay, the 2 that are right obtuse, or if you've got 3 angles, and if you've got at least 2 that are right or obtuse, if you sum up those 2, you must be at least 180 degrees. And then, of course, when you add in the third angle, you'll exceed 180 degrees, which is impossible. So by the triangle angle sum theorem, it follows that every triangle has at least 2 acute angles. And then this follows immediately. It will be very important for us. It's so obvious at this point that perhaps it's not worth the trouble, but it does come up. And it says this, it's the right triangle corollary. If you've got a right triangle, let's say ABC with its right angle at C, the other 2 angles are acute and complementary. Well, as for the fact that they're acute, that follows immediately from the other corollary. This is like a corollary of a corollary. Every triangle has at least 2 acute angles. Angle C is not an acute angle, so angles A and B must be acute. And then, of course, they're complementary, right? Because the sum of angles A, B, and C is 180, but C takes a 90-degree bite out of that 180, so it leaves 90 for A and B. So, of course, they must be complementary. And then finally, here's a very nice little result that comes up very often later on. It's the equilateral triangle corollary. We knew previously, we were able to prove previously in the chapter on congruence that an equilateral triangle must have 3 equal angles, but we were not able to say anything about what the measures of those angles must be. We can now say, of course, that they're each 60 degrees, and that's just a simple matter, of course, right? If all 3 angles are equal and they sum to 180 degrees, they must be 60. 180 divided by 3 is 60 degrees, so there we go. All right, that's it.